So this is the lecture 10 on module theory. This lecture on Artinian module. In previous lecture, we discussed on different modules and quotient module, submodule, and now there's a new type of thing concept. It's called chain condition on module, and this some chain condition module is hold or not hold. That depends on that. Or depending on that, we classify that module as Artinian module or the Noetherian module, like that. So this is on Artinian module. Now, chain condition on modules. There are different chain condition on module. So we first have the chain condition, descending chain condition, sometimes like DCC. So we say descending chain condition holds for submodule of an R module M. Here R is take as a R with unity. So R with 1. We always assume R with 1 may not be commutative, and you can assume commutative for simplicity. R with unit element 1. Now, this is the descending chain condition, chain. So, descending chain of submodules, M1, M2, Mn, dot, 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 they are submodules of M. And then once this submodule has some descending chain, say M2 is a subset of M1, M3 is a subset of M2, and dot, 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 then this chain must be stationary. That is called the descending chain condition. M is stationary means that after some step, say F100, M100, M100 equal to M101 equal to M102, like that. So after some step, that submodule must be stationary, must be constant. It can't be go infinitely submodule, proper submodule. It can't happen. It may happen. If it is not happening, then it is called descending chain condition. In descending chain condition, after some step, it will be just stationary. If it's not so, if there is we have a chain such that is a proper submodule, then we say this descending DCC not hold. One more chain condition is minimum condition. What is the minimum condition for him? Now, any non-empty family of submodule has a minimal element. So here it is just a chain. It is just a chain, but here is any collection of submodule. It may not be subset, submodule, or maybe disjoint, any collection. So more general. This is a more general type. So you can take any collection of submodule, and in that submodule, family of submodule, there is a minimal element. This is may or may not be hold, but if there is a minimal element for every family of submodule, then it's called minimal condition. So now the theorem is this two condition is equivalent. So surprisingly, these two conditions are equivalent. So second condition slightly generalized. So what is the proof? The proof is first we prove 1 implies 2. So we assume that there is a descending chain condition hold, and we have to prove that that minimal condition also hold. Now consider any family. So take a script F is a family of some submodules I in some family index set I. So it is a family of subset, family of submodules, and be a non-empty family. It's a non-empty. It's a non-empty family. So at least one element must be there, non-empty. Submodule, that F is non-empty. Some family of submodule. Now, take any I one of this. Take any I1, and consider this MI1. We have to find a condition chain because we have to use that. We assume that the 1 is true, so descending chain condition is true. That means we have to construct a chain and then use the descending chain condition, and that. After then we can say that this is chain is stationary, and using that we will show that there is a minimal element is there. So okay, we have to construct a chain now. So take a I1 of this any index, any index. You can take any one. Now take that corresponding submodule MI1. Now if MI1 is minimal, if it is minimal, then done. If it is a minimal, MI1 is minimal, true. We are true because minimal element exists. But if MI is not minimal, then what happens? If it is not minimal, then what happens? If it is not minimal, what is the meaning of that? So not minimal means there is a one more submodule of that. Say it is a I2 in the family, and this MI2 not equal to MI1, proper submodule. So now this is the since it is not minimal, so we have a MI2. Again, if MI2 is a minimal thing, then we are through. We got this minimal element. If it's not minimal, then mi3, then again mi4. We have a chain, descending chain of this. If somewhere it is a minimal, we prove it there is a minimal element. If not there, if not a minimal element does not exist. If we assume that it's minimal, it does not exist. So assume that minimal element does not exist. So if we assume that minimal element does not exist, what happens? Assume that minimal element does not exist. Minimal submodule or element of this collection does not exist. Then what happens? Then there is a proper subset of that chain, that proper, MIN, and they are going on. But descending chain condition holds for this M. But it can't be true. It can't be infinitely a sequence of infinitely many terms that each are distinct. It can't be true because the descending chain condition after something must be equal. So there is a condition. This is a condition. If we assume that this family of submodule is not a minimal element, then descending chain condition does not hold. So it is actually contrapositive statement. And if somebody got this minimal element, we are through. So this proof 1 implies 2. Now what is the 2 implies 3? 2 implies 1. Now we assume now that any submodule family has a minimal element, and we have to prove the DCC hold. So to prove DCC hold, we first have to take the chain of submodules, descending chain. Now consider this is the family. This is the family. The family is all set of all these MI. Now this family, all this, no need of taking constructive family. The 2 implies 1 is rather easy. You take the whole thing, all submodule of this chain is as a family. Now this family has a minimal limit. We assume that minimum condition hold. So this have a this has a minimal element. So say it is MR. MR is the minimal. And what is the meaning of that? The meaning of this is if you take AMS, which is that in descending chain condition, if S is this, then what happens? Then that must, since MR is minimal, that AMS must be MR for all x greater than R. So since it is the minimal thing, so DCC hold. So 1 implies 2 implies 1 is rather easy. 2 implies 1 implies 2. We have to just take some. We have to construct a descending chain. Now there are two conditions are actually equivalent, but is apparently looking that second one is more general. The first one is apparently looking is weaker, but actually equivalent. But apparently looking the second one is stronger, but not that they are actually equivalent. But if this such a thing holds, two theorems are equivalent, but apparently one is stronger, apparently one is weaker. What is the use of that? The use is this: when we have to show something is Artinian, something DCC or something hold, we show that DCC hold. That showing that is rather easy because it's a weaker condition. But once I know this is a DCC hold, to prove something, we apply that minimum condition because it's apparently a stronger condition. So when we want to apply some this thing, we use the second one, but we have to prove this thing. We prove the first one. That is not for this particular equivalency. All this equivalency actually for this purpose. So equivalence 1 implies equivalent to 2 means someone is apparently weaker. So to prove something. Prove these two conditions, we prove 1, but when you use this one, we use actually 2. Now Artinian module that satisfies DCC condition. If that satisfies DCC condition or minimal condition, same thing. This module is M is called that Artinian module. Now minimal submodule exists in non-zero Artinian module. Now there is a minimal submodule exists in non-zero Artinian module. Why? Because we take all this family, take that all submodule of this M. Since it's a family of submodule, this minimal submodule exists. So minimal submodule exists for any non-zero Artinian module. So it is trivial. So example, module with finitely many submodule. If it's a finitely many submodule, oh, if it is finitely many submodules, that chain, any descending chain must stationary. It can't be distinct because it's a finitely many submodule. The whole sequence cannot be distinct. So since it's a finitely many submodules, so finite abelian groups is actually the finite abelian groups is a module over Z, and this has a finitely many submodule. So this finite abelian group is the set is finite. This whole module is finite. Then there can't be infinitely many disjoint distinct submodules. So this is an example. Finite dimensional vector spaces. These are also example of Artinian module. Why it is so? Now it is a infinitely many element, but since the finite dimensional, we know if it is a proper subspace or module, that module is now a subspace, submodule is now subspace, that dimension must be strictly less than that. So if mi is mi plus 1 is a submodule of mi, then the dimension must be less than or equal to mi, dimension of mi plus 1. And if it is a not, the dimension is equal, then it is a equal subspace. And if the subspace is not equal, that means a proper subspace, the dimension must be strictly less. And since it is a finite dimensional, after some time the dimension will be just fixed. Now if dimension is equal for mr and ms, and if ms is subspace of mr and dimension are equal, then they are must equal. So in vector space, a subspace which is same dimension must be the equal. It can be less, some proper subspace. So this infinite dimensional vector space are this, but infinite dimensional vector space is can't be never actually. Infinite dimensional vector space, this is not Artinian. So no, it is not just an example. This is for all infinite dimensional vector space. This thing is vector. This is not Artinian. Why? So if V is a infinite dimensional vector space, then we have a V1 is a subspace which is infinite dimensional. Then again V2 is a subspace, proper subspace, which is infinite dimensional, and so on and so forth. So if it is a countable, so it's a proper. Sorry. So if it's a countable basis, say take it as a countable basis. So take as a V1 has a countable basis, say some V1, V2, dot. Now take V2, B2 is a, just start from V2. And just this is V1 is actually some span of B1, and V2 is a span of B2. So like that. So any Bn is starting from Vn, and this Vn is just the span of this Bn. Now this is not a equal, it is a proper subspace. Now you can generate infinite sequence which is not stationary. So that's why the infinite dimensional vector space is not Artinian. Similarly, the infinite cyclic group, say Z is the infinite cyclic group. In that case, Z is the infinite cyclic group generated by 1, then generated by 2, generated by the set of all even integers, the set of all integer multiple of 4, that is up to 2 to the power n. Then this is a chain is actually proper subspace. It's proper. Is a proper. So it's not Artinian model. Now some important result on Artinian model, that submodule or quotient module of Artinian module is Artinian. Why this is so? Why this submodule and quotient module are Artinian? Now let M is the Artinian module and N is a submodule of that. N is once I write N is a subset, that means a submodule. Not only just subset, is a submodule of M. Now N is family of submodule of N. Now collection a family of submodule of N. This is family of submodule of N. Is also submodule of M, because N is itself submodule of M. Now this has this family has a minimal element. Sorry, that yes is a minimal element. Why this is a minimal element? Because this is the family of submodule of M also. So this is a minimal element. So that's why N is Artinian. And what about this quotient? Why this quotient is also Artinian? Say any descending chain. Now proof is by 1. We are using proof is by 1 and by 2. And now we using for quotient module we use the 1. This is the condition. We here use the minimum condition. Now using this is the condition, we prove that any quotient module of Artinian module is Artinian. So consider a descending chain of submodule of M mod n. So there is a descending chain of M mod n. So what is like this? This is something like say n1 mod n, then n2 mod n, like that. And if this is now n1 into n dot n1 into dot dot this submodule is a submodule of M. Now these are the minimal element. Then and this is stationary. Not only the minimal element, using DCC it is a stationary. So we use this. Now this implies actually n1 say this. Now this is stationary, so after some step this will be equal. And so once this is equal, then this quotient also equal. And that implies this quotient also equal. So that's why the submodule of quotient and quotient module are Artinian. Of the Artinian module is again Artinian. Now there is an important theorem. If a module in the conversely it is sort of converse, is a module which is such a has a submodule n, which is n is Artinian and this quotient also Artinian, then M is Artinian. So if M is Artinian, then n is Artinian and M mod n is Artinian. That is easy. That is the first result. The next one is slightly tough. It is complicated. It's not trivial, non-trivial thing. That if there is a submodule which is Artinian and that a corresponding quotient module also Artinian, then M is Artinian. Then and from that we can easily prove that every non-zero submodule of Artinian module contain a minimal submodule, because it's an Artinian module, so any submodule is again Artinian, and since it is Artinian, that submodule is Artinian, so it is contain a minimal submodule. Now to prove that second one, what we have to prove, we just take a descending chain. We will show this is the condition hold for M. Now we take a chain. Let this is a chain. This is a descending chain. Now we have to prove after some step it will be stationary. Now we consider this thing. So n intersection with M1, n intersection with M2. Dot. Now this is stationary. This is stationary because it's a submodule of n and n is Artinian. N is Artinian. So this is so since these are submodule of n and n is Artinian, this after some state will be stationary. So therefore some r this will be equal. Now we have to use that quotient also. So how do you quotient? You can't take that M1 mod quotient by n, because M1 may not be the submodule. So we have to take this one, this as a submodule of M and then quotient by n, because it is a n contained in n plus M1, and then we have this chain condition on this quotient module. And once this has a chain condition, the quotient module, then again this is after some state is stationary. So some ms may not be same r, that is same after some step. Now we use that the maximum of the m and s, and if we take the maximum of this m and n, which one is bigger, will that we actually these are two are same. You can take a, s and r is as same. So if r is 100 and s is 200, we will take 200, r as 200. Now what you have to show, so we can take this as a r also. Without loss of unity, we take the same r. Which one is bigger? We take that r as a r. Now from this too, we have to show that mr is equal to mr plus 1. So since these two are equal, what happened? This MR plus 1 is a submodule of that dot dot for all. Then this now what happened? Now yes, so and n that is also equal. So this intersection are equal with n, and one is a subset or submodule of the another, and we have this thing, this one, and this one, all these three. And one thing we have to use that is important. This no, this will be plus. Sorry, this will be plus. Right. Sorry. These are equal. Now these are these two are equal. And these three condition hold, and we know there is a theorem in previous lecture. We know that if this quotient by n is isomorphic to actually MR quotient by n intersection MR. This is true. This is not for this case. This is always true for any submodule thing. Now this is so. Therefore, these two are isomorphic. So that means n MR quotient by n intersection MR is isomorphic to MR plus 1 quotient by n intersection MR plus 1. These two are isomorphic, and the quotient thing is equal. The quotient part is equal is by this first one. That means your MR and MR plus 1 is isomorphic, but MR is a MR plus 1 is a submodule. So in a submodule which is isomorphic, that must be equal. So put together all this thing, we have this MR equal to MR plus 1 after some stage, and after that. So we prove this the second thing. So very important result. Now there's a more result on Artinian module. Is this sum and direct sum of finitely many Artinian module is Artinian, but direct sum of infinitely many Artinian module is not Artinian. Is not only for every infinite direct sum. It's not for just, there is an example. For some direct sum of infinitely many Artinian is Artinian. For some direct sum of infinitely many, in some cases is not Artinian. Not that. Every case, like infinite dimensional vector space, every infinite dimensional vector space is not Artinian. So every direct sum of infinitely many Artinian module is not Artinian. But what about the sum? If it is not direct sum, no. Sum of infinitely many direct distinct Artinian. If it is not distinct, then it is actually equal. But if it is distinct Artinian, take the infinite sum, not the direct sum, then maybe it is Artinian. Why it is so? Well, the third one is actually trivial. Why? But we just take say R2. R2 is a vector space. Vector space is a Artinian module R2, since it is finite dimensional. Now take the there's infinitely many line passing through origin, but they are distinct. So these are different submodule or subspace, infinitely many submodule or infinite subspace of V is R2. Now this V1, V2, V and the infinite collection of this is a one-dimensional vector space over R. This is Artinian, and the sum is actually the V. So it is again Artinian, but this sum is not direct sum. For it is, if it is direct sum, then dimension will be increased and dimension will be infinite. So if a infinite direct sum of Artinian module or is a vector space thing, if it's a finite dimensional vector space, if you have a direct sum of infinite direct sum of finite dimensional vector space, that infinite direct sum is actually infinite dimensional. That's why it is not Artinian. That's the idea. But for sum, because it is actually taking infinite sum, but actually it is a finitely many finite sum of finite direct sum basically. So infinite sum is actually finite direct sum. So that's why this is happening 3. So it is actually more generally true, not only for this module. In vector space is also true. If you take the sum of infinitely many subspace, this actually may be some finite direct sum. Even it is distinct. Even it is distinct. Now, what about this direct sum of infinitely many Artinian module is not Artinian? It's again it's easy, because if since it is a M1 M2 say these are infinitely many infinite direct sum. Now take this as a my first one. Then we just drop say one thing. This is a proper. Then again drop one more. Again drop one more. So again it is a proper submodule, but this never end up. You can just proper, and never is stationary. So it is not Artinian. Now to show sum of or direct sum of finitely many Artinian is Artinian. How do you show that? That first take say M1 M2 is a finite collection of Artinian submodule of M. Is all a submodule. Once I write subset is actually submodule. Now take this sum. Take the sum. So once I show this for sum, then it is also true for direct sum, because direct sum is basically a sum. After all, it is a sum. So we just show for sum, then it is true for direct sum also. So for sum, we have to show that n is Artinian. We will use the induction. So if n equal to 1 by induction, it is true, because this M1 is Artinian. We assume that M1 M2 M10 are Artinian. Now we use the induction. So we assume that it is true up to n minus 1. It is, we know for it is up to n minus 1 it is Artinian, and Mn is Artinian. Just we have to show that this plus this is Artinian. So sum of two Artinian ring module is Artinian. We have to just show this is Artinian is by assumption is a hypothesis step, and as you already given that Mn is Artinian. So we have to just show the sum of two is not the finite. The sum of two Artinian is Artinian, then sum of any finite is Artinian. So take this as I say n dash. So your n is actually n dash plus mn. So m dash, assume it is Artinian, mn is given to be Artinian, you have to put n is Artinian. Now what is n mod mn? This is actually n dash plus mn, which is n quotient by mn, and this is isomorphic to n1 by this isomorphism theorem, third isomorphism theorem. This is so. Now, which is a n dash is Artinian, and this is a quotient of n dash, quotient of n dash, and we know that the quotient of any Artinian module is Artinian. So this is Artinian. So n mod mn is Artinian. Now this is n dash is Artinian. Is assume that, and so quotient of Artinian is Artinian. So it's isomorphic to n mod mn. So m quotient by mn, that is Artinian. Now n mod mn is Artinian. Mn is Artinian. By the previous theorem, if the quotient module is Artinian, the submodule is mn is Artinian. N mod mn is Artinian. Then n is Artinian. That is given in the second one. So m is Artinian. So that's why from this to this is Artinian. So mn is Artinian. N mod mn is Artinian. So therefore, this implies n is Artinian. So it completes the proof. And direct sum is just a consequence of the sum, because direct sum is itself a sum. After it is a sum. So this completes today's lecture on Artinian ring, Artinian module. Next video will show the Noetherian, about the Noetherian thing.